Okay, so now that we've seen how to calculate the flux integral, and I hope you had a go at question 1b yourself. Okay, make sure you do have a go at it yourself. You can always check the solution after, but make sure you have a look at the previous video and you're comfortable with solving question 1b. Okay, so now we're going to look at the divergence theorem. Divergence theorem, or Gauss's divergence theorem. Okay, so what does it say? Well, it says that the surface integral, or the flux across the surface, so calculating the flux across the surface, as we've learned, is the same as calculating the divergence of the vector field in a solid over a volume. Okay, so what does that mean? If I have my object that looks like this, say, okay, it's a 3D object. Okay, well, it's saying that the flux through the surface, okay, so that's how much of this vector field is perpendicular to the surface, calculated at every point on the surface. Alright, even the base going perpendicular down because it's a flat base, so how much of the vector field is going perpendicular down on the base, even on the side. So that's the flux, and it's saying that it's equivalent to finding, so I'll try to draw this again. Yep, that's not a bad recreation. So that's the flux, so that's the left hand side, is calculating that. Whereas the right hand side is, well, we know how to find the divergence of a vector field, and we can calculate what that quantity is at each point. Okay, it's not a vector, remember, it's a scalar. The dot product gives you a scalar, so it's a quantity. So we just have to find that at each point, represented by these green dots. These will be numbers, and they'll depend on what position of x, y, z we are. If we calculate the divergence at each point and sum it over the whole volume, so this is not just on the surface, these are on the surface, these are inside, then these two things are equal. So if we calculate the divergence at each point, sum it over the whole volume, these two things are equal. Okay, why are they equal? Well, it's a what goes in, what goes out sort of thing. What goes in must come out sort of problem. Okay, so if the divergence is non-zero, that means at each point there's a little bit more of the vector field going in than out if it's positive, and vice versa if it's negative. Okay, so say the divergence of the vector field is zero, so that means no point swallows anything. It's sort of all energy is neither created nor destroyed. It just passes on from one point to another. So that would give that vector field would definitely have a divergence of zero. Then it means that overall what goes in must come out. Nothing's going to get stored. Hence the flux over the whole surface must be also zero. Okay, so if the divergence is zero, the integrand is zero here. So clearly the flux will be zero. The triple integral of zero is zero. So the left hand side will also be zero. And that makes sense because what goes in must come out. So if you've got a whole surface here, if you calculate the net flux over some given time period, then it must be zero because none of the energy is sort of stored, or if you think about an incompressible fluid, it won't compress in one point. Okay, so the net flux must be zero. That's just a loose introduction to the divergence theorem. But what we're going to learn now is how to calculate the right-hand side integral and verify the answer. Okay, and verify means we have to work out the right-hand side, the left-hand side separately, and show that they're equal to each other. Those questions require the most work. But sometimes, in the previous question, we learned how to calculate the left-hand side. Sometimes that's a complicated integral. Sometimes it's just easier to do the volume integral. So we'll look at both of those cases in the next couple of videos.